It begins with silence. A diver descends into a blue expanse where sunlight fades into twilight. The water thickens, pressure deepens, and the world narrows to the slow rhythm of bubbles. Beneath the surface lies something vast, a shape too geometric to be natural. Not a reef, not a ridge, stone laid by human hands long ago. For centuries, stories of cities lost beneath the sea have lingered between myth and possibility. From the sunken ports of ancient trade routes to entire settlements claimed by rising tides, the ocean has long hidden traces of human history. Today, those stories are no longer confined to legend. Modern sensors, instruments of light, sound, and magnetism are giving shape to what the water has concealed for millennia. This is the story of how technology is transforming our search for underwater cities. 1. The ocean's hidden archives. The ocean is Earth's greatest archive of forgotten worlds. Over 70% of the planet's surface lies beneath water, and much of it remains unexplored. For thousands of years, coastlines have shifted, sea levels have risen, and river deltas have migrated. Entire landscapes that were once dry land now rest under waves. Valleys turned into seafloors, plains now mapped as continental shelves. Archaeologists have long suspected that early human settlements once stood where the sea now stretches. But until recently, those suspicions were nearly impossible to test. The ocean conceals with silence, visibility fades quickly, and depth resists exploration. Traditional diving methods could only reach a fraction of what lay below. To find a city beneath the sea required more than courage. It required the ability to see through darkness and distance, to reconstruct worlds hidden in the deep. That is where modern sensors enter the story. 2. From murky waters to digital maps. The first breakthrough came with sonar, sound navigation and ranging. By sending pulses of sound through water and recording how they echo back, sonar reveals shapes that light cannot. In the early days, these echoes appeared as faint lines on paper charts, rough outlines of the seafloor. But as computing power grew, sonar evolved from simple depth readings into detailed topographic images. Multibeam sonar now emits thousands of sound waves in a fan-shaped pattern beneath a research vessel. Each wave measures the depth of the seafloor at a different point. When combined, they form a 3D model, a landscape of underwater valleys, slopes, and structures rendered with astonishing precision. Where earlier explorers saw only shadow, scientists now see the contours of walls, streets, and columns. Ancient harbors appear as symmetrical arcs. Collapsed temples resemble stone mosaics resting on sand. The ocean floor, once abstract, has become a digital map. With these tools, researchers began to revisit regions described in old coastal records and myths. The submerged ruins off the coast of Greece, the ancient ports beneath the waters of Egypt's Nile Delta, the forgotten trade cities of the Indian Ocean rim. Many of these turned out not to be legend at all. 3. The discovery of Herakleion. At the mouth of the Nile, buried under layers of silt, lies one of the most remarkable finds of recent decades. Herakleion, an ancient Egyptian port city lost for more than 1,000 years. Once a bustling hub of trade, religion, and culture, Herakleion vanished beneath the sea sometime between the 2nd and 8th centuries CE. For centuries, it existed only in scattered historical references, a name on ancient scrolls, a rumor among sailors. In 2000, a team led by underwater archaeologist Frank Goddio used a combination of magnetometers, side-scan sonar, and sub-bottom profilers to survey the Abu Qir Bay. The magnetometer detected anomalies, subtle distortions in Earth's magnetic field, caused by metal or dense stone structures beneath the sediment. Sonar imaging revealed shapes too symmetrical to be natural. And sub-bottom profiling, a technique that sends low-frequency sound waves through layers of sand, revealed buried walls and foundations. What emerged from the data was astonishing. A vast grid of streets, temples, docks, and colossal statues, perfectly preserved in the seabed. Each sensor reading told part of the story. When combined, they reconstructed an entire cityscape, silent for over a millennium. Herakleion had not disappeared. It had merely moved from the visible world into the realm of sediment and sonar. Modern sensors brought it back, beyond Earth, testing grounds for future worlds. The technology used to explore underwater cities has applications far beyond our planet. NASA and other space agencies use the same types of sensors to test techniques for exploring icy moons and extraterrestrial oceans. Underwater ROVs designed for archaeology now serve as prototypes for missions to places like Europa and Enceladus, worlds that may harbor oceans beneath their frozen crusts. Each dive into Earth's underwater past doubles as an experiment for future planetary discovery. The ocean, in this sense, is both a time capsule and a laboratory. Yet, as technology extends our reach, new questions arise. How do we protect fragile remains from exploitation or looting once they are mapped? Underwater archaeology now operates within strict ethical frameworks. Data collected by sensors must be shared responsibly. Precise coordinates of sensitive sites are often withheld to prevent unauthorized dives. Digital models allow researchers to study and share discoveries without disturbing them physically. These advances have transformed archaeology from an extractive pursuit into a form of stewardship, preserving memory while minimizing intrusion. Across continents, the pattern repeats. Human settlements hugging the coast, rising seas reclaiming the land. In Southeast Asia, sonar has revealed remnants of early cultures beneath modern bays. In Northern Europe, LiDAR and magnetometer surveys have traced prehistoric shorelines now flooded by the North Sea. And along the coasts of Japan, underwater surveys continue to investigate mysterious stone structures near Yonaguni, formations that may represent either geology or the remnants of human craftsmanship. Whether natural or cultural, each discovery deepens our understanding of how intimately human history is tied to shifting waters. Every submerged street is a reminder of change, of worlds that once thrived above the waves. Today, when a new underwater site is mapped, it rarely stays confined to scientific archives. High-resolution data are transformed into digital reconstructions. Using virtual reality, researchers and the public alike can now walk through cities that no longer exist in air. Temples rise again from data points. Market squares echo once more with digital footsteps. These reconstructions are not mere simulations. They are evidence-based resurrections, built from sonar grids, laser scans, and geological surveys. They allow us to experience history not as ruins, but as living environments shaped by tides and time. In this sense, modern sensors do more than find underwater cities. They restore them to collective memory. A new generation of technologies promises to take discovery even further. Real-time 3D sonar systems now stream images directly from the seafloor to research vessels. Swarm robotics allows fleets of small autonomous drones to coordinate, covering vast areas in synchronized patterns. Quantum magnetometers can detect minute variations in magnetic fields, revealing hidden objects deeper than ever before. And machine learning algorithms are beginning to predict promising regions for exploration based on geological and historical data. In a few years, entire coastal zones may be mapped continuously, revealing submerged sites faster than any previous generation of explorers imagined. Each improvement shrinks the boundary between the known and the unknown. Despite these advances, the ocean keeps its secrets carefully. Pressure crushes, salt corrodes, and currents shift sand like a restless tide of time. Even with the best sensors, much remains obscured. And perhaps that is what makes every discovery so powerful. Each sonar image, each magnetic anomaly, each faint outline beneath the waves is not merely data. It is a glimpse into memory. The sea remembers the footsteps of people who once lived where we now swim. It holds the stones they raised, the ports they built, the streets where their stories unfolded. Modern sensors are not just instruments of detection. They are instruments of remembrance. We find ourselves in a new age of exploration, not by conquering distance, but by revealing depth. Underwater sensors transform the opaque into the visible, the forgotten into the known. Through pulses of sound, flashes of light, and patterns of magnetism, they allow us to hear the faint echo of civilizations that time tried to erase. And yet, even as we illuminate more of the ocean's floor, one truth persists. The sea remains vast, and its silence endless. Somewhere beneath those waves, beyond the reach of sonar or laser, lies the next epic discovery, waiting patiently in the dark. Because the ocean never truly forgets. It only waits to be seen again. The greatest challenge in underwater archaeology is not depth, but obscurity. Most ruins rest beneath layers of sediment, sand and silt deposited by centuries of currents. To uncover them physically risks destruction, so scientists rely on non-invasive imaging, allowing them to see through layers without disturbing the site. Sub-bottom profilers act like medical ultrasound for the Earth. They send low-frequency sound pulses into the seabed and record reflections from buried layers. The result is a cross-sectional image, a window into what lies beneath. These sensors can reveal foundations, roads, or ship timbers buried several meters under sand. Combined with precise GPS positioning, they produce maps accurate to centimeters. In effect, researchers can now perform a virtual excavation before a single diver enters the water. This method preserves fragile sites while guiding archaeologists towards the most promising locations for limited recovery dives. It is slow, deliberate work, part science, part detective story. While sound-based sensors dominate deep exploration, light still plays a role in shallower waters. LiDAR, light detection and ranging, uses laser pulses from aircraft or drones to map coastal seabeds where the water is clear. When combined with satellite imagery, it can reveal submerged walls, roads, and harbor outlines extending from modern shorelines. In areas like the Caribbean and the Mediterranean, LiDAR has uncovered networks of ancient docks and causeways barely visible from the surface. The technology's precision is so high that even slight variations in stone alignment can suggest architectural design. Meanwhile, underwater photogrammetry has revolutionized visual documentation. Using thousands of overlapping photographs captured by autonomous underwater vehicles, AUVs, software reconstructs 3D models of entire sites. Archaeologists can then explore these models virtually, rotate them, and even simulate how the city might have looked before it sank. Light, once defeated by water's opacity, now returns through computation. As depths increase, human divers reach their limits. Beyond about 100 meters, pressure becomes dangerous. Visibility vanishes. Here, robotic explorers take over. ROVs, remotely operated vehicles, are equipped with cameras, sonar, and robotic arms. AUVs, autonomous underwater vehicles, operate independently, scanning wide areas with precision. They follow pre-programmed paths, weaving across the seafloor like mechanical cartographers. Each sensor aboard these robots collects a different kind of data. Multi-beam sonar for mapping terrain, magnetometers for detecting buried structures, chemical sensors for analyzing sediments, high-resolution cameras for detailed imaging. Artificial intelligence then processes this data, detecting patterns the human eye might miss. AI can identify geometric regularities, right angles, circles, grids that often indicate human construction. It can also differentiate between natural rock formations and carved stone. This marriage of robotics and machine learning has transformed exploration from random search to targeted discovery. Entire coastlines can be surveyed systematically, revealing structures once invisible to history. As discoveries multiply, a new picture of ancient coastal life begins to emerge. Many early settlements were built near water, rivers, estuaries, and shallow bays, for trade, fishing, and fertile land. But these same regions are vulnerable to rising seas and seismic activity. Over millennia, climate shifts and tectonic events submerge them gradually or suddenly. In the Mediterranean alone, sensors have revealed dozens of ancient ports now under several meters of water. The Greek city of Pavlopetri, considered one of the oldest submerged towns in the world, the Roman harbor of Portus Julius near Naples, and the Bronze Age ruins off Israel's coast. Each city tells a story, not only of culture, but of environmental change, a record of how humans adapted, migrated, and rebuilt as the sea advanced. By combining sonar mapping with geological analysis, scientists can reconstruct ancient coastlines and estimate how fast the ocean rose when earthquakes struck and how populations responded. What emerges is not just archaeology, but climate history written in stone.